Hello boys and girls, welcome to another episode of FoulkesBrau. So today we've actually got quite a nice project to do. So I thought I'd share this with you. It's a project I have to do for college, and it's based on an idea that a friend gave me back home in South Africa. So those of you in South Africa will know that you have issues with load shedding and problems like that. So what most people do is they put solar panels on the roof, and they have big battery banks with inverters, and during the outage time they are running off the battery bank power. The problem is that the battery banks are not usually sufficient to do everything that you'd like to do. So what I mean by that is you wouldn't be able to run everything normally as you would, because batteries are expensive, and let's face it, most people are not millionaires. So anyway, the proposed circuit I never got around to designing was basically to monitor the state of the batteries, and as the battery charge declines, to switch off the different AC mains plug circuits. So what I mean by that is to actually switch it off or isolate it in the DB board, not the individual plug itself. And this actually came about by, it was actually quite humorous. It was a joke because this friend of mine, so he had a fairly small battery pack in, but what would happen is, so he'd go to work during the day, and his wife was a stay-at-home mom, and you wouldn't know if the power was off, so she would carry on as normal, and the battery bank would be pretty much drained by the time he got home in the evening, and they would sit in the dark. So this is to actually prevent that sort of thing. So in other words, for the guys, it's to keep your beer cold. So the plug circuit that your beer fridge is on, your wife shouldn't know about, and if she goes and puts the kettle on, it will switch off that plug circuit, and if she goes and puts the hairdryer on, it will go switch off that plug circuit, etc, 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 because let's face it, things like dishwashers and washing machines and kettles draw a lot of power. So to sort of explain it, I have this basically a system block diagram. So what we are actually designing is the stuff here in the blue block. So you would have a battery bank and invert with a DC bus, your inverter, an AC bus, and that will go to your AC circuit. So that's external to what we're trying to do. So what we need to do is we need to take power from the battery bank, and we need to do some sort of protection and conditioning on it, generate some voltage rails for different voltages that we might need in the circuit, and ultimately power a microcontrol unit. The micro will control the AC mains. I think we'll probably go solid state. I don't want to go relays. The micro will also provide a web interface so that you can actually see what's happening in the system and set it up. And basically you have the software engineering component of that, and you have some signal conditioning. So that's pretty much what we're going to try and design. What is important to note is these battery banks are normally, the DC bus voltage will be running at about 56 volts, around there. The problem is when you start charging it, it will go up to about 60, maybe a bit more. That's the typical configuration I've seen. And that's because of the way that the solar panel cells are configured. So I've talked enough about this. I think let's get to the important stuff. So what's important is we need to take this 70 volts, and our microcontroller is ultimately powered by 3.3 volts or 5 volts, but the micro itself will be 3.3 volts. I'm going to use an ESP32 because it's just easy for this, and ideally I would have liked to use the PIC microchip PIC, but there's issues with their Wi-Fi chip, because I don't want you to have to go through the cloud. The idea is that this can be a little access point standalone, and you can do what you want with it. So I'm going to use Altium because as a student I get a student license for it, and is quite a powerful package. For those of you playing along at home, you probably want to use KiCad, KiCad. The steps are a little bit different, but it's the same idea. So I've already started downloading some components and just placing them here. And I thought, well, instead of me carrying on like a madman and just finishing this and you guys don't get to see it, I'd actually walk through this with you. So the first problem is we need to get our 70 volts. Well, I'm going to base it on 70 volts from our battery pack, and we need to get it down to some workable voltage. Now the easiest way to do this, I must add, I'm allowed to do this with surface mount components, so that changed the whole design thing, so it made it a lot easier for me, so I don't have to do a whole lot of analog manipulation and stuff like that. So the easiest way to do this is to take a DC to DC converter, and it's not a very, well, it is a bit complex, but it's easy enough to understand. I've selected this LM 5085. We can see what applications are automotive, infotainment, battery supplies, or super capacitor chargers and LED drivers. But what is interesting to me, it's got a wide input voltage range, 4.5 to 75 volts, which is brilliant. We've got current limiting. We can select the frequency that we want it to run at, and we don't need loop compensation. So this is quite a nice package, and that's typically the circuit that you would put together for it. But what was interesting to me is the where are we? The power dissipation. So basically this package can dissipate quite a lot of power without me having to go and try and put in external heat sinks and stuff like that. So that is also a very big consideration. We're not going to be using a lot of power. I think probably half an amp at 3.3. So probably the total power draw will be about 1.5, 2.5 watts, which is not too bad. Anyway, we've talked enough. If you go through this data sheet, you will see that there are a lot of calculations and stuff that you need to do to work out the different components you might want to put in. In other words, we need to calculate values for this input capacitor, timing resistor, these adjustment capacitors, the inductor sizes, etc., etc., and the flyback diode. Now the nice thing with using a Texas Instrument chip, if you use a well-known chip, if you go to their website, you will get a thing like this, which is a calculator. Obviously you would do well to check the calculations, but for now I've done some smart checks. I'm very happy with it. So I've put in some general parameters to see what component sizes we want to use. So I've put in our input voltage as a maximum of 70 volts. Our nominal voltage, in other words where it should be running, is about 52, and the minimum voltage we're going to put in is 15 volts. Our target, our output voltage we want is 15 volts. The maximum load current we're going to say is 1 amp. We will never get to the 1 amp, but we're going to say it's 1 amp. Minimum load current, we're going to go about down to 100 milliamp. It'll probably be a lot less than that. The first thing we have to do after we've put that in is calculate these feedback resistors. So what you see here, it creates a voltage divider. That the voltage divider feeds back into here, and it gives it a reference to tell it work harder, work less hard, to give us our output voltage. So I've put in an upper feedback resistor of 20k. It counted I put in 1.8k, and that will give me 15 volts out, 15.1. I can go up to 1 megahertz with this chip. I don't want to create design headaches for myself when I do the board layout, so I've settled on a nice conservative 200 kilohertz as the switching frequency. I chose a P MOSFET to suit this, and you have to go look in the data sheet for these on and off delay times, and that will give you a calculated resistor, this RT resistor here, which is the timing resistor. Based on the current and everything else, it spat out I need an inductor size of 300 microhenry, and obviously you've got to put it in and it will give you the peak current. Now we want this thing to operate in continuous conduction. In other words, there will always be current flowing through the inductor. We don't want it to ever drop to zero or to get saturated. The current limiting scheme we're going to use is this current sense type 1. So what that does is it will measure the current going through the FET and out, and if it gets too much, it will switch the chip off. It will, so if you've got a short circuit or whatever, it will limit that current going through. We could have used the second scheme here, where they actually use the RDS on value of the PFET, but that has issues, so we'd rather put in a separate sensing resistor. It's cheap as chips and off we go. So that will give us our current limiting. We've got to give it some input ripple that it will allow, and it will give us, based on a lot of all these other things up front, it will give us what the required input capacitance is here. This will, even though we're getting our battery bank here to power this thing, this chip will pull power, although it won't really affect our battery bank, because batteries on that scale are massive. So it reckons we need about 10 microfarads, so I'm going to go, let's see, and it also recommends that we use ceramic capacitors, so I'm going to probably just put 3 of them, so I'll put, let's say, 14.1 microfarads of capacitance in. Then we've got to look at which output ripple scheme we want. We're going to go with scheme 3. In other words, we want the least amount of ripple out of it, and it will give us some values, and we can carry on from there. So for the capacitor, so we would go again 14.7, and it will give us some more calculations, and ultimately it will spit out some values. So we're pretty much going to put out almost 1 watt, or just about 1 watt of power in our device. So we've talked enough, let's actually get to the schematic. So like I said, I'm using Altium. I've got some of the components, and what I really want to do is I want to let's get this input capacitance in. We said we're going to go with 14.7, so that's 4.7 microfarads by 3, or 14.1, sorry. So the way we do that is I am using DigiKey because it's just much easier. I don't want to go and try and build symbols and stuff. I'm using the 1206 package, and I'm using surface mount. You always want to make sure it's in stock, that they have a CAD model, and you want to make sure that it's an active component. So I'm going to take off the what have I got here? Mounting type, product status, okay. Stocking and media. So I'm going to select 4.7 microfarad. Let's see what it gives me, a whole 1. The big thing, this voltage rating, as I'll show you again, we've said that this input voltage can be up to 70. So your capacitor has got to be, the voltage rating has got to be higher than that. Normally we would double that, but they've only got 100 volts, so that's fine. So what I'm going to do, I'm going to look for the cut tape. You don't, and I'm just going to copy that part number. You don't want to buy the reels and the tape and reels, because you're going to end up buying quantities of 2,000. We don't need that many. So we'll go to Altium. I will open this little thing on the right, panels, manufacturer part search. Let's get rid of that one. We'll look for it. And what's nice is it's got the symbol, the schematic symbol, it's got the footprint and the model. We're going to go to DigiKey, and am I in the right place? I'm going to go to this download, and I'm going to select place. I will close this. I'm just going to copy that. I'm going to go to my schematic library, and I'm going to paste it here. So what we can see is it's put this in. I just want to change a few things. So I will go back to DigiKey. I'm going to copy the DigiKey part number. I'm going to delete that, put that in there. The comment, well, I'm going to just put the size 4.7, and I'm going to copy this short description. Now, what's nice is we can see by doing that, all this data is down here. The cost, who it's from, the footprints, all those things are there. So I'm going to save everything. We'll go back to our power supply. We'll go to our components, and we need this one that we just created. So I said, well, I didn't say, the device worked out that we needed 10 microfarad. So if we put 3 4.7s in parallel, we actually are adding the capacitance. So that will give us the 14.1. So I'm just going to put 3 of them in parallel. I'm just going to zoom out. I'm going to move everything across. What is important, or if you're a CD like me, you'll see that there are numbers in the vertical columns, 1, 2, 3, 4, 5, 6, 7, and numbers or letters in the horizontal columns. When you're laying out your circuit, you would ideally, well, not ideally, you want to use these vertical and horizontal axes as references. So I'm going to go 3B for now. So you see my components nicely placed in there. all placed in there, and I'm going to put my 3 4.7 microfarad capacitors just there. What I don't care about is the pin number. These are not polarized, so it really, I don't think we need to display them, but I'll leave it for now. We can turn it off later. So we've got our 3 capacitors, and if we look at where we have to put them, well, it's going to go in between VN and ground. So let's leave a nice bit of space here. And I'll come 1 down. I have a ground point that I've put in the circuit. I'm going to just put it in the middle of the chip for now. And I'm going to put a wire in. So I'm using shortcuts, but the way you could do it is you can right click up on this icon up here. You can place a wire, a bus entry, a net label, whatever you want. So I'm just going to use the shortcuts. And let's come down. And connect these. I'm going to move the ground over because I like it there. And the other thing is I'm going to just move these capacitors down. Let's put them in the middle of the chip. It just looks better on the eye for me. This EP pin 9 is an exposed pad. It's the bottom of the chip. And because this is a surface mount chip, the bottom of this chip is metal, and you will create a metal pad that this will be exposed to, and you would solder that metal pad to the bottom, well, to the board, and the heat dissipates through there. Okay, we also need to connect our ground from the chip, so I'll come out 1 and go across. So what have we done? We've taken care of this input capacitance. We still need a supply. We need this bypass capacitor. So, and we need this timing resistor now. The bypass capacitor, typical 100 nano or 0.1 micro. And the timing resistor was calculated for us based on our frequency and everything that we need at 462.76. So I've actually downloaded them. This one I'm going to delete. We have our capacitor and our timing resistor. So let's drag that across. So how did they connect it? So the timing capacitor goes between V and RT. There's a shutdown pin. If you pull that pin to ground, it will shut this thing down. We don't want to do that. So we're just going to have the resistor between VN and RT. How are we going to do this? I think it could go there. We could move these capacitors across a bit more. Let's see how it looks for now. We'll put a wire. I'm going to move it one across. So we've got 4 in that block, so let's do this. 1, 2, 3, and we'll move these 2 across. So that's just me being pedantic. I like things to be symmetrical. So we have done what? We've got that, we've got that, we've got that. So RT is done. We just need to put in this bypass capacitor, and that's going to go between Vin and ground. So what I will do is I will move these over another 4. We'll put him in there, and we'll put a wire like that. So we could probably move this over a little bit more. It's still in 3, the capacitors will be in 2, and then 1 we can have our input. We can probably come 1 down with this. Okay. What we might want to do is actually put some notes here. So I'm going to put a note. I just want to move this ground over. So we're going to say Vin. I wanted to make it less than 70 V DC. What else do we want to know about this? We want to know the switching frequency, 200 kilohertz. We can add more design notes as we go on, and I'll put it below the chip. Okay, well, if it wants to be like that, then I will have one block on either side, that's fine. Right, so we have the input, we have the timing capacitor. We need to supply the chip with power. Well, they've recommended a 40.47 microfarad. Now that doesn't make sense between VCC, from Vin to VCC. It doesn't make sense. Let's have a look at the data sheet. No, it is like that. Okay, so and let's go to Altium. We'll go to our components. I don't think I have a 0.47. No. So we'll go through this again. So we'll take out the, okay, it's taking it out for us. So let's say 0.47. Okay, I know what it's doing. Because it thinks I've selected a value. So we want 0.47 microfarad. Okay. What is happening here? nonsense is this? Okay. So the other thing that is important, you'll notice I'm using an X7R type capacitor. That's for the temperature coefficient. In other words, the temperature, ambient temperature or temperature around this does not affect this capacitor too badly. It's actually quite stable, which is very important. So 29 cents, 30 cents, 31 cents. Okay, let's just take the Kemet. Again, we want the cut tape. We'll go to Altium in our schematic designer. We've got our panels, manufacturer part search. We'll clear this one. We'll paste it in there. So this time it doesn't give us any option to download it. Not a problem, we can go and do this. We already have a model for it. So what we can do is we can go in here, manufacturer part search. We will import. So notice I've gone to DigiKey. I'm looking for the unit where they will give me 1. We'll import it and it will create a blank schematic for us, but it will have all the details. So our DigiKey part number is right. We're going to copy the short description. We'll put our short description in. Capacitor, so it's C question mark. Comment 0.47 U, because I want to know the size. We'll go up and we'll just copy this symbol. We'll paste it. Again, I don't want to see the pin numbers. So I'm going to save that. I'm going to do the same for here. I'm going to just take off that pin number. I'm going to save them all again. And I'm going to take it off here. We'll come back. Where is our component? That's 10. I don't see it. I did save it, I'm sure. C12 by 647. Okay. It is there. One more thing, I don't want to see those pin numbers, so let us update the components from the library. We'll go next. This should be fine. No, I didn't do what no, keeps opening. we want to execute the changes. Close. I didn't hide it. Okay, I thought it would have. Oh well, doesn't matter for now. Right, so we need to go and see where we want to put this. So it's going between VN and VCC. So we'll put it up here somewhere. And then that will go out to our adjust and our sense side, or our iSense. Okay. So we'll come up with a wire. Let's see, maybe we'll move that into 4. Yeah, like that. And we're going to move it 1 down, and we'll move the wire 1 up. Maybe 2 up, 1 up. It's fine. Okay, so that takes care of that. Now we need to do the current limiting. So they want 1000 picofarad. Okay, that's fine. With our adjustment resistor, which we've said we're going to put a 50 milliohm. That's this one, 50 milliohm, and then our adjustment, we're going to use 2 kilo ohm. Okay, so we need to get capacitors again. So we want 1000 pico. We'll go back to DigiKey. We will get rid of the capacitance. Thousand pico. We just take this Kemet one, 22 cents. Well, worth 10 cents. You see that's tape and wheel. Oh, it's got cut tape. Oh well, let's see if we copy it. We will go back in our manufacturer parts search. We can place it. Nice. Close this. Copy it. Go to our library. Paste it. And what we'll do is go and get the data from DigiKey. We want the cut tape. Wait, this is 1000 pico. And we want to put the part number there. A short description, get rid of, and then get the DigiKey. We'll copy that. We'll paste it. There's no pins showing. It's fine. 732.12104. We'll go grab it. Okay. So that will be this capacitor. We need adjust. That's a 2 kilo ohm resistor. Let's see if we can get that 2 kilo ohm. I should have something open for resistors already. We'll kill that. So we want 2 kilo ohm. That's the nice thing about using surface mount. There is such a wide variety that we don't get with the through hole anymore. We just take this Jaeger. We'll take the cut tape part number. We'll go here, manufacturer part search. And it doesn't give me the option to place it. Not a bother. We'll go here, panels, manufacturer part search. We'll take this first one, and we want the digi key with the single units. We'll import it to the library. We'll change our designator. And what did we say it was? We said it was 2 kilo ohm. So we're going to put it to K. Get rid of this and put in our short description. Copy. Paste. Now we need a symbol. Well, I've got one here. We'll copy it. And where is it? It's this one. We'll paste it. Like that. We'll save it. RC1206 FO. We've got our power supply. And we'll drag it in. That capacitor we can get rid of. So these two are going to be in parallel. Let's see, how do they want us to connect this? Okay. I should probably get this R-Sense. And we said 50 milliohm. So let's get a 50 milliohm. So even if I had 50 milliamps and I had 1 amp flowing through it, well, it's 50 milliwatts. So we are fine. Okay, these guys have got cut tape. It's 36 cents. Mache. 1% will be fine. So we'll copy the cut tape. Chances of us getting a part for this are not grand, or getting a symbol. So we will come here, panels, manufacturer part search, paste. got 14 providers. We'll go with the DigiKey for the unit price. Import. It's 50 milliohm. So it's 50 milliohm. I'm going to call it like that. Get rid of that description. We'll copy a short description from DigiKey. We'll save it. We'll copy. And we will paste. So we can go back to our power supply. And there she is. So I'm going to rotate it. I'll press space. If we zoom out a bit, let's see. I'll just save. So how do they want us to connect this? So we've got to come to the adjust pin. So we've actually got to come. Oh, this is horrible. Okay, maybe if we do it like that. Yes, I think maybe we can put it here. Let's just make sure of this. Okay, so I'm going to move this off screen because you don't really need to see this anymore. It just makes it easier for me to work. So I'm going to come out with our wire to there, to there. This is, okay, that's fine, so I can go down one. Nice, I can come down one. And I can come out with a wire like that. And that means this can go one across. That actually looks okay. So it's feeding through the capacitor. Is this 1,000 or 100? I just thought I can fix that. It's 1,000. So through our adjust, which is 2K. Right, this has got to go over here. I don't want to move the designator. And that's got to go to iSense. So I'm going to just rotate it. So this is going to this is going to be messy because it's going through here as well to the gate. Well, not to the gate, to the source of the FET. Which means this is, oh no, this is horrible. Or maybe not, maybe not, maybe not. This looks a bit this is the wrong way around. So let us rotate this thing, or mirror it, not that way. We're going to have to rotate it 180 degrees. Then mirror it. That looks right. Yes, that looks right. So the drain is this side. So this has got to be like this. It's got to come off there. So we're going to go through there to there. I'm going to leave space of 1 for now. I'm going to come off there. And that's got to come to here. The problem is that this will come up one like that. Yeah, so this is driving our gate. Doesn't look too bad. What I can do is move you across. You're still in 4. I can move you across, and you across. And then that allows me to move you and you across. And we can just move that across. Yes, I'm a bit OCD. Okay, so that fits nicely in 4. Right, so now we need to connect the inductor. And we are almost done with this circuit. So we've got an inductor, we've got some feedback resistors, and we need a diode. So we're going to need something that's very fast. So we are going to use something like like a Schottky, I think. I think we will use a Schottky. So let's go back to DigiKey. I'm just going to open this in a new tab. We'll go to products. What do we look at? Products. Passives. Semiconductors. Discrete. Diodes. Well, we don't want arrays. We don't want bridge rectifiers, and we don't want RF. So we'll go for single. We want Schottky. Okay. In stock. You must have a model. Must be active. surface mount. Of course, we want to be able to solder this thing, so the package is going to be, actually, let's do this. 1N5819 SMD equivalent. Okay, but what are they calling this thing? Okay, that doesn't help me. They've given me some sort of, let's see. Let us see. Oh, it doesn't help, they're obsolete. 60 volts, 10 amp. Okay, well that gives us an idea because 60 volts. So let's go up from 60 volts. I really don't think we're going to need 10 amp. We did calculate the peak. At 1.1. So let's go up from that. Sod, all the sod packages. Let's see what we can take out here. There are 1206s, that's fine, and D2 pack. Let's see what we've got here. So I'm just looking for something that would be easy for me to solder. And this looks just like it. We could go with that. It could give me 100 volt 1 amp. Fast recovery, that's fine. I'm actually thinking of going for this D2 pack. Although I don't need a 20 amp or 30, 2, 8, 115. Two amp. You know what? I might just go with this 1206. think, yeah, price-wise, the others are double. And we're not going to have, just out of curiosity, what is the power dissipation in this thing? Okay, that's fine. RMS voltage, DC blocking. .75 degrees C per watt. You see, the thing is, we can probably push almost a watt of power through this. Right, so I think that takes care of that. Sorry, we are going to have to use a D-squared pack. So let's just take off. Let us take off the supply device package. We'll take out the 12x6. And then we will go for the cheapest. 100 volt, 8 amp. 750 millivolts. Okay, so do we want SMC, ST? I'm gonna go with ST. It's 5 cents more. Right. Cut tape. Let's go back to manufacturer part search. Oh no. I don't want to go and draw a diode. Let's see, what has it got here? Ha. So we want it for Altium. We'll save it here. Let's open that. Where is it going to put this? There. Okay. So there is a way to do this. We can say run script or browse from file. Symbols, data sheets, there we go, Altium Designer, we want that. I just want to make sure that we're looking at the right thing. Yes. Run that, and that didn't do anything. Run script. Oh, so what it's done is put this thing off. to make sure. And we're looking for this one. We'll import, yes, I don't care about that. And what it's done is created this. Okay, so let's go to the schematic library, and it's given us a symbol. Okay, so let's go to here. We'll go to our library. Get the cut tape part number. So we in our library, yes, panels, manufacturer parts search. And there's our friend. We want the one with unit prices. Import. Our designator is going to be D. I'm going to get the manufacturer's part number. Which is there. I'm going to get the short description. Which is there. And then what I'm going to do is just go back here. Okay, so we've put it like that. I'm just going to copy that. I'm going to paste it exactly like they've pasted. Okay. We'll say view football objects. Save all. So we've got an STPS. This one I'm going to close, we don't need it. We'll come to our components, choose our library, and there's our rectifier diode. It's a bit big compared to everything else, but okay, how does this get placed? Let's rotate it. I'm going to hide that port number. And basically our rectifier diode sits like that. It is going to go to ground, so what I'm actually going to do is I'm going to rotate it again and again. So it's going to be sitting something like that. Let's bring this down. We'll drag that across. And that one's not connected, apparently. So now what we're going to do is drag this down. And I'll drag you up. I'll connect you like that. Wish I could move this a little bit over. Not quite. I think what I might do is go and edit this symbol and get rid of this block. Okay. doesn't matter. So that takes care of our switcher. Now all we need to do is to take this feedback circuit, our voltage divider feedback, and go to this pin here. Okay, so that's easy enough to do. We're going to do that, we're going to do that. Our feedback will come let's see how would this yeah, okay, so we're going to come there like that. That gives us our voltage feedback. So this has got to come to ground. Still leave that there. What I can do is just copy that symbol for now. Put a wire on. And that is basically our output voltage. So what I'm going to do, I'm going to place a power pin. I'm going to call it VCC because it's our power port. Oh, you know what, I'm not going to call it VCC, I'm going to just get another one. It's not 12, it's going to be 15. That's that. So that pretty much takes care of that. We have got, we just need to put in a connector here, a fuse, a voltage divider, and we are done. So we will get our battery voltage coming in here. So all these components and things that we've calculated, some smoothing here, some timing resistors, and ripple rejection. Through these current sensing and adjustment pins. Current sensing, why is that? Oh, it didn't move. Okay, no problem. Just connected in. Through our switching element, the PFET, our rectification element, our inductor, our magnetic storage, and generating our output voltage of 15. This voltage divider splitting the voltage to give the feedback here. So this should be about 1.25 volts. And as long as it can keep 1.25 volts here, it will alter whatever it needs to do to make that 15. And we're going to switch at 700 kilohertz. So I'm not going to bore you to death anymore with this, what I'm going to do, because I've just got to put in a few linear regulators and things, some connectors and stuff, and then we'll come back when I put, well, basically I'll lay the rest of the stuff out, and we'll come back when we start doing the board layout. Anyway, thanks for watching. I hope you enjoyed that. I hope it gives you a bit of insight into how we try and be lazy and not do things too complex. Anyway, as always, take care, be safe. Cheers.